Welcome back. This is the second segment in section 1.2. As you recall in the previous video, we were starting to develop the idea of some geometry results, and we had started into this discussion about triangles. I just want to reiterate that we are talking about, whether it's obvious or not, we're talking about Euclidean geometry. So we're not talking about weird surfaces or things like that, which is really just beyond the scope of a class like this entirely. But to be careful, there are some other sorts of ideas that are out there, so don't take this as absolute literal truth in all situations, because there are situations where it just doesn't hold. But for the most part, I mean, we have to start somewhere, so we start where the Greeks did, which was a flat space that's infinite and blah, 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 blah. So as you'll recall, we had just stated that there were these things called interior angles of triangles, and that the measure of triangles, the interior angles, is always a positive number, but it's always less than 180 degrees. And there is a sort of a really sort of big result that comes out of that, or not really out of that, but it's kind of what's driving that, which is, and I will do it without proof because it's very hard to prove. I mean, you have to, it's not something that you can just kind of whip out in 5 minutes and hope that everybody understands what's going on, but so be it. So one very important result is that, I think we're on page 3. So this is an important result. The sum of the 3 interior angles of any triangle always adds to exactly 180 degrees, okay? Now, when we're actually measuring things, we end up with some rounding errors and some experimental measurement errors, but this is sort of a mathematical result. It turns out it is equivalent to the Euclidean parallel postulate statement, and there are ways to demonstrate one from the other or vice versa, but this is something that you already knew this, but I'm reminding you of that. So that's kind of a last statement that we have on our triangle business, and maybe some more statements about lengths now. So here's a fact. The length of any line segment is measurable and is unique. That's kind of a fancy way of saying that there is one and only one way to measure the length of any line segment. And if you get into other mathematical structures, it's related to the distance function. Of course, you know what the distance function is for Euclidean space. It's like, it's the Pythagorean theorem ultimately, and that's kind of where we're headed. But based on this fact, when we have lengths of line segments, unique just means that any one line segment has exactly one number that represents its length. So we're going to talk about this sort of zoo of triangles. So types of triangles based on 2 possibilities. We can either talk about their angles, or we can talk about their lengths of sides. So based on angles, we have acute triangles. And what is an acute triangle? Well, this is where all interior angles are acute. And you remember acute means that they're between 0 and 90 degrees, non-inclusive. We can have right triangles, where one interior angle is acute. Sorry, is right. Now, because everything adds up to 180 degrees and no angle measures 0, this is guaranteed that there is one and only one interior angle that can be right. It's sort of a consequence of, if you had two right angles in a triangle, they would never meet on at the third vertex, because those two lines in flat space are parallel. And that's sort of a consequence of the alternate interior angle theorem, right? Because those 90 degrees, you'd have alternate interior angles that are equal, and so they must be parallel. Finally, we have what's called obtuse, and these terms are used to say like an acute triangle, a right triangle, an obtuse triangle. One interior angle is is obtuse. Now, when you have one obtuse angle, that means it's more than 90 degrees, which means that based on the sum of 180, you're automatically going to get that the other two angles have to be acute. But anyways, we'll use these terms, so it's important to know what they are. But it basically only has to do with, that one special angle. So acute, that seems pretty obvious. They're all less than 90 degrees. Right, you have one right angle. Obtuse, you have one obtuse angle. And the consequence of either one of these is that everything else is acute. We could also have names based on lengths on sides. So we have the term scalene. And this is no sides equal. No sides have equal length. We have isosceles, which is two or more sides equal. So I'm running out of space, so I'm going to just use an equal sign. And then finally, we have, now notice two or more, we have equilateral. All sides equal. So it just so happens that all equilateral triangles are also isosceles. Isosceles happens to have some neat properties in geometry that kind of crop up, and we sometimes use them to sort of prove some other stuff. Okay, so I hesitate to keep going, but I think we have a little bit of time left on this before we get to a huge number. But let me just add a couple more statements here. So on page 4, I believe now. Two triangles are said to be congruent if the corresponding angle pairs are equal, and the corresponding sides are 2. So this is kind of a consequence of congruence. And you could talk about their measure being coterminal and the lengths equal, whatever, but I think you understand where we're coming from. This really is more of a geometry concept. So what this is saying is that now it turns out that there's also an equivalence of area. So if two triangles happen to be congruent in the Euclidean space, then their area is the same as well. It's a little bit more challenging to prove that, but it's something that we'll use. anyway, so congruence is kind of a stronger statement than the next one, which I'm going to pull out, which is to say that two triangles are similar if the corresponding angle pairs are equal. Or I really should say are congruent, because that really gets to the heart of the statement. Okay, so it turns out that if you have pairs of congruent triangles, then those triangles are also similar. But similarity does not guarantee congruence, at least not in Euclidean space. So these are concepts that you spend like usually an entire year talking about in a high school geometry class, and so I won't bore you with the details of what all that stuff means. But here's what I am going to refer to is that there is, I mean, this is the requirement, is that all the sides have to equal and all the angles have to equal. But we know that there's some shortcuts, and I'm just going to go ahead and write those down. So geometry results. The following are minimally required, to prove congruence of triangles. And I want you to be familiar with the notation. We have what's called the side, angle, side, side, angle, side. Now, what does that mean? That's where you've got, you know, two triangles where side is congruent to corresponding side, other side is congruent to corresponding other side, included angle is congruent to included angle. Okay, so side, angle, side, that leads to congruence. So if you have this arrangement, then all the other sides and all the other angles correspondingly are equal. Another one that comes up is the so-called angle side angle. And we could kind of use the same triangles here, or something that's similar. And in angle side angle, we now have, you know, we have an angle that's congruent. We have another corresponding pair of angles that are congruent, and then we have an included side. That's the angle side angle. The arrangement of the A and the S is critical to this. Another one is what we might call angle side. This is the shorthand for it. And so in this case, it's where we have congruent angle, and it's not the included side now, but actually another side, an opposite side. This forms that this side is said to be opposite of that angle. Okay, so those got a couple more here. The so-called side, 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 which is where we have two triangles where corresponding sides are congruent. And this also leads to congruence. So if all the sides are equal in a corresponding fashion, then all the angles are as well. And it's the position of these angles that's critical also. You can't just say, well, this angle is equal to that one, or something strange like that. Now, there are three other, I mean, there's two other types of ways that we can arrange the sides and the angles. And it turns out that one of them is the definition of similarity, which doesn't guarantee congruence. And the other one is kind of a unique case. It's the so-called side-side angle. And so I want to be careful here. These do not lead to congruence, right? But in side-side angle, it leads to two possible arrangements. So let me just draw these two triangles. And kind of show you why it doesn't work. Okay, so side-side angle is where you have an angle, and then you have two other sides. Angle, two sides. And notice that you end up with this possibility, at least, of creating two triangles that have those requirements, side-side angle, but are not actually congruent. And that should be pretty clear from what's going on there. Now, one thing that you do note is that there are certainly situations where you may not end up with a problem, because if this angle happens to be obtuse, then you can't have this sort of mess up that happens. Or if this side's longer than that one, you know, there's some situations where this is okay, but in general, side-side angle will result in two possible solutions, or at least it can. We'll talk about the criterion for that and how to deal with that in section 7.2. So that's a little bit down the road. Also, another one that does not work is the so-called angle, angle, angle. Now remember, that is the definition of similarity, but let me just kind of sort of real quickly show you why it doesn't work. Now in this case, we're sort of stating that all these angles are congruent with each other, but notice they are much bigger in size. And so similarity does not give you any kind of congruence, but it does give you something that's far more valuable, which is something called the fundamental theorem of similar triangles, which is the basis for why all of trigonometry works. We'll come back to that in the next lecture because it does get kind of a little bit convoluted. So here, very briefly, I will discuss the fundamental theorem of similar triangles, consequences of similarity, and then I have an example problem that's in the textbook that sometimes throws students for a loop. So I will see you back here.